Hello. This video is about section 9.4, which is called convergence tests, although there are a lot of convergence tests, and only a couple of them are mentioned in this section. Let's just jump right into this first one. This is called the divergence test. And this is a test you can do right away to check almost instantly if you have something that diverges. So remember, when we're dealing with the series, we're dealing with this attempt to add up infinitely many individual terms, A1 plus A2 plus A3 plus A4, going on forever. And we want to know, does this actually give us some sort of answer because the partial sums have a limit? Well, if these individual terms are not particularly small, then it's impossible to add them up, right? Even if they're, small but not microscopic, if they're approximately one tenth plus one tenth plus one tenth plus one tenth plus one tenth, going on forever, is going to be infinitely big. So the only chance we have for convergence is if the individual terms get smaller and smaller and smaller, approaching zero. So this is what the divergence test says. If the limit of the individual terms is not zero, then we have divergence. Just right off the bat, it is absolutely impossible to add these up if they're not getting microscopically small. Now, if the limit of the individual terms is zero, it might converge, but it might diverge, right? We're not sure. This is, when I learned this was called the preliminary test. So it's just something you can do right away. And maybe you'll notice immediately, wait a second, these terms are not getting small. I know I'm dealing with a divergent series, so I don't have to do any other tests. Okay. Um, Before we do the next test, we're going to go over some basic facts. So if we're dealing with a convergent infinite series, we can add two series or subtract them or multiply by a constant, and we'll still have a convergent series. And the sum will be what we'll expect. So just as a quick example, if I had the summation as k goes from 1 to infinity of 1 over 2 to the k minus 5 over 4 to the k plus 1. Assuming these converge, and we'll figure that out, we're allowed to just break this up. We can do this series, and we can do this series. And it might be easier for us to figure out what's going on if we treat these separately. It's never a bad idea to write out some individual terms to get a feel for what's going on. In this case, we will notice that both of these are geometric. Here we have 5 over 16 plus 5 over 64 plus 5 over 256, etc. So they're both geometric. The one on the left has r equals 1/2. The one over here has r equals 1/4. So this one, it's a over 1 minus r. This one is a over 1 minus r. So the one on the left is 1/2 minus 1/2, which is 1. And this is 5/16 over 3/4, um, which is 5/16 over 12/16. So this is 1 minus 5/12. And this whole answer is 7/12. So you're allowed to break things up and rearrange them according to your intuition, assuming you're dealing with convergent series in the first place. I'm not going to prove this. It's just kind of a fact floating around in the background. And another important thing to keep in mind is that the convergence or divergence of a series is not affected by finitely many terms. Convergence is about what happens in the limit. And if we have some odd behavior happening for a finite number of terms before a pattern emerges, that's fine. So as an example, if I have, just sort of some random behavior for a while, but then a pattern emerges, and I notice that this part is convergent geometric, then the whole thing is convergent. because whatever happened before I got to the pattern that I recognize, this is just a finite number. So I can add this finite number onto what I would have gotten otherwise. So sometimes we will notice that we're doing things where it feels like the pattern does not happen immediately. Maybe one or two terms at the beginning have some sort of weird exception. If the question is simply, does this converge or not, that's not going to affect the answer. Okay, so now we're going to have a really powerful test here. This is called the integral test. So let's assume that we have a series with positive terms. Right? We're going to deal with negatives in a couple sections. For this section and the next, just assume everything is positive. And let's assume that they agree with some continuous decreasing function f. So the idea is whatever formula we have, we can think of as basically being an example of a familiar continuous function. It needs to be decreasing or at least eventually decreasing. So if we're thinking about this infinite series versus this improper integral, right, they both involve some sort of accumulation as we're going out to infinity. This one is literally adding things, a1 plus a2 plus a3 plus a4 plus a5. This one is a more continuous process, but we can think of it as an accumulation of area. Here's the thing. Either they both converge or they both diverge. And I'll give you a gist of what's going on here. So I'm going to make a little graph. Here's one, here's two, here's three, here's four, here's five, here's six. And let's imagine this here is the point at 1 comma a sub 1. And this is the point at 2 comma a sub 2, and 3 comma a sub 3, etc. We're assuming this is decreasing. Well, our assumption here is that these values agree with some continuous decreasing function. So this is f of x. So here's what I'm going to do. I'm going to draw some boxes. So here, this box in red, we will notice, oops, I do want this. This box in red, it's 1 unit wide and its height is a1. So the area of this red box is a1. And then if I draw this box, it's 1 unit wide, but its height is a2. So its area is a2. And I could keep doing that. So the red areas would be this series, the summation as k goes from 1 to infinity of a sub k. Now, let me draw some green boxes. Here's my green box. This is kind of like left endpoint approximations and right endpoint approximations. This first green box, it's 1 unit wide, and its height is at a sub 2. So the first box here has a height of a sub 2. And then my next box has a height of a sub 3. And then the next one has a height of a sub 4, etc. So the green areas would be all the same things, except I'm missing the first one. So k starts at 2. And what we'll notice is that the improper integral is this area under the curve starting at 1. And what we can see from our picture is that area that we're trying to figure out is smaller than the area of the red boxes, but bigger than the area of the green boxes. So I'm going to squeeze this in somewhat awkwardly. This is our improper integral. But here's the thing, either these two both converge or they both diverge, because they're the same thing except for one extra number. And this is between them. So either these are both finite numbers, and therefore this is a finite number in between them, or they're both infinitely big and this is infinitely big. So that's the gist of this. Let's look at an example. Determine if this series converges or diverges. So right off the bat, we can say, all right, this is like f of x equals 1 over x cubed. And I'll just observe that the limit of those individual terms is 0. So this thing at least has a chance of converging. Right? It doesn't have to, but at least it's eligible. So what we can do is we can convert this to the corresponding improper integral. And we know that this is actually a limit. So this is the limit as k goes to infinity, the integral from 1 to k of x to the negative k. So my new exponent is -2. So if I plug in k, I have -1/2 times k to the -2. Then I have 1/2 here. And so what's going on is k is growing infinitely big, but here I have k in the denominator. So this part here is approaching 0, and the whole thing is 1/2. So what that means is that this one also converges. This converges. So this converges. And we're not saying it's equal to 1/2, right? What this is equal to is a much harder problem, but it's definitely finite. Now, what we saw here is an example of what's called a p-series. So by definition, if we're dealing with a positive number p, our p-series is a series of the form 1 over 1 to the p, plus 1 over 2 to the p, plus 1 over 3 to p, plus 1 over 4 to the p, etc. And when we have a p-series, it would pretty much always follow this pattern. We could convert something to a negative exponent. We would do an antiderivative in which we bump it up. And if after bumping it up, we still have a negative power, then the part with the k goes to 0. But if bumping it up turns it into a positive power, the part with the k gets infinitely big. So here is the rule worth knowing. When we have a p-series, and you should just know this as a vocabulary term, if p is greater than 1, right? So that means our denominators are kind of on the big side, which means our fractions are small. It converges. And if p is less than or equal to 1, it diverges. Right? And you want to just know this. You don't want to have to be figuring this out. You should know the term p-series. You should be able to recognize a p-series when you see one, and you should know almost instantly, am I dealing with a convergent p-series or a divergent p-series? Same with geometric. We want to have a very small number of familiar series that we just know everything there is to know about. So when we see other kinds of series, we're ready to make some comparisons to things we understand better. So make sure you really know this. Okay, that is the end of this section.